Happy morning, dear friends. Here's yours, Dr. Ajanta. Welcome to Demystify with Ajay. Dear friends, here we are going to discuss about the evaluating or assessing, we can just specify, assessing the performance of each model that you train before you decide to put it into production. So, yes, of course, by end of this session, you will be able to create an evaluated data set. So you will be equipped to assess the performance of an regression model. Maybe let me just, we are going to discuss on about a linear regression. So linear regression model by using mean absolute error and mean square error. And yes, of course, let me just discuss each and every part of this particular matrix functionalities. Okay, and yeah, dear friends, when you assess the performance of a model, you look at certain measurements or values that tell you how well the model is performing under certain conditions, and that helps you make an informed decision about whether or not to make use of a model that you have trained in the real world. So some of the measurements you will encounter in this session are, that is yes, mean absolute error or R square error. So yes, each and everything we are just going to see. And of course, dear friends, next in forthcoming sessions, yeah, we would discuss how to train a model to perform this sort of regression and all the concern techniques. And yes, you may start by training one model and then evaluating how often the prediction from the model are correct, and you might then proceed to train more model and evaluate whether they perform better than the previous model, whichever you just created. Okay, and dear friends, actually we have already seen an example, more of the things related to train test split in this previous. And of course, you should note that it is important to split your data into one set that is used for training a model, and the second set that is used for validating the model. It is this yes, validation step that helps you decide whether or not to put a model into production. But here we will go one step further and split into three. Yes, one to train a model, one to evaluate the model, that is during training, and one to evaluate the model before putting into the production. Okay, so now let me just have a data split with the different sets, and you may proceed to train and evaluate the model. Okay, now dear friends, today it is the session all about assessing model performance for regression models. Performance for regression models. See, when you create a regression model, you create a model that predicts a continuous numerical variable. So when you set aside your evaluation data, yeah, you have some that you can use to compare the quality of your model. So what you need to do to access your model quality is compare the quality of your prediction to what is called the ground truth. Okay, so which is absolute or we can just specify actual observed value that you are trying to predict. Okay, so let I just give you a small demo onto that. So yes, so let I just go here. It is an actual and it is prediction. And yes, let me have some records, 5 records. Kindly just to see here, this would be our actual, and here we have something as prediction, and this is actual, and let we have prediction. This is our third one, and 4.440, 3.109 and 2.95. Let me fifth one like this, 4.987. So see here, dear friends, actually this line 0 in the output compares the actual value in our evaluation data sets to what our model predicted. So the actual value from our evaluation data set is 4.89. The value that model predicted is 4.132. So, and seems to be the same thing for line 1, that is compares 4.194 and 4.364. So here in practice, the evaluation data set will contain a lots of record. So you will not be making this comparison visually. Instead, you will make use of some equation. You would carry out this comparison by computing a loss function. And the loss is the difference between the actual and the prediction. So in data mining, actually this is specified as like distance measure. So there are various approaches to computing distance measure. So that gives rise to different loss functions, maybe as like Manhattan distance or Euclidean distance. And of course, there are various loss functions for regressions also. But today's in this session, we are just going to discuss about mean absolute error, which is mainly on Manhattan distance, and mean squared error, which is mainly on Euclidean distance measure. Okay, so actually the goal of these function is to measure the usefulness of your model by giving you a numerical value that shows how much deviation that is between the ground truth and the predicted values from your model. Okay, yes, dear friends. So yes, your mission is to train a new model with consistently low error or lower the error. Okay, so that is what we are just going to discuss. So the first of all, what we are just going to discuss today is, let me just start with R squared. Yes, we are just moving about this, I think so. Mean absolute error, mean square error, root mean square error, log error. So there are so many things is there. One by one, let me just discuss it, and we just go with the coding. Okay, so see here, dear friends, this R square. Okay, so R square, that is pronounced as like sometimes called the score, and measurement, the coefficient of the determination of the model. So think of it as the model's ability to make good and reliable prediction. So this measure is accessed using the score method of the model and is available for every model. So your goal is to train successive model with a higher R2 square. So higher R2 square, of course, here if I just specify, if I just want to give you as like this R square, kindly just see here, this exact score can have the range that is between 0 to 1, and yes, your goal is to try and get the model to have the score that is close to this one. Okay, so close to this one. So first of all, let me just go with this R squared. Okay, and here coming to this program, so here I have just given you some important libraries as like pandas, which will use to read your data, and also import train test split, of course, which you will use to split your data into training and validation set. And here, dear friends, I have just used this linear regression, which you will use to train your model. Okay, so let me just train our model. So I just execute this. Okay, so as I have already specified, yes, R square is an important factor in evaluating the performance of a model. So we are going to take it towards the linear regression, and here one such data which we are just going to use is, of course, FIS toxicity data set, and this exact data set is taken from UCA machine learning repository. Okay, and I just share this exact data set and to the program I have just uploaded in GitHub, and in the description I just share the link also. And dear friends, before going on to this, let I just include the data here. Okay, so here this is what header. Why I have just specified that header it is, see, kindly just have a note. This is our data set. Okay, and towards this data set, kindly just have a note of to the first First one. So this exact CSV file containing the data does not have the first row that contains the column header. So you proceed to read in the file and store it in a variable called that data frame. So you specify the list containing columns, that is the headers, by passing it into the names parameter. So and kindly just have one more note. Even this is as like a comma separated variable. So here the exact separator, it is not a comma, it is a semicolon. So this exact CSV uses semicolon as a comma separator. So you specify that using the separate parameter, and let me just make use of this. So here we just go. So yes, dear friends, so this is our header and we are just making use of this data set, and here I have just specified the separator. So let I execute here, and yes, sorry, this is actually a data. Yes, it's done. Okay, so now kindly just have a note, dear friend. We want to have the what about the columns? So I just specify this CIC 0. Actually, it is the information indices. Okay, and next the SM1. It is exactly a 2D matrix based descriptors. And the next one GAT-S1I. It is actually 2D auto correlations. And next NDSCH, it is Pimpale's Promelis, and NDSSC, actually it is atom type counts. MLOGP, it is molecular properties, and next the last, it is quantitative response. Okay, so this attribute represents the concentration that caused death in 50% of test fish over a test duration of 96 hours. Okay, yes, so this is the exact data set we are including for our session as like an data. So let me just have a look onto this. So this is what. Okay, yes, so by using this head we are having our top 5 records. Okay, now what is the next one? Of course, we have to split the data set into futures and labels. What it is, futures and labels? Yes, it is as like the X parameters, the independent and dependent variables. Okay, so if we want to split it into training and evaluation database. Okay, so sorry, data sets. So here this is the futures and here the label, it is the target. So we are just splitting the data, and same yes, you can create 2 numpy arrays also. So here it is as like an numpy arrays, which is as like futures and labels. You can then proceed them twice 8. Okay, so the first split, it is all about the training data, and the next it is training data and evaluation, and the second split, it is all about validation and then test data. And yes, I just execute this. Okay, now what it is? Yeah, we are just going to create a linear regression. Yes, dear friends, till actually, of course, till now we didn't discuss about what is the model and what is the mathematical intuition behind this linear regression model. But anyhow, yes, once we finishing this evaluation, we would just move on to the or algorithm one by one. Okay, so machine learning algorithm one by one. So here coming that creating a linear regression model, let I just execute it. And kindly just to see here, dear friends, you are creating an instant of this linear regression and storing it in a variable called model. And you will make use of this to train on the training data set. And kindly just to see here, we are using this fit method. By using the fit method and training data set, yes, that which you have already created in this one. So this is what our data. And yes, of course, here we have the parameters as like futures and labels. And by using this, we are making that X train and Y train, that is to be trained. This is the model to be trained. So let me fit it. So yes, here we done. And next here we are just going to make a prediction, and that exact prediction, it is all with X value. And kindly just observe, dear friend, we are making a prediction, that is use of validation data set. Okay, so validation data set to make a prediction. So this is stored as like ypred, so y underscore pred. Okay, now let I execute. Okay, now next, yes, we are just going to compute this R square. This exact R square is computed using the score method. Okay, so this is what the score method of the model. And the next one here, we are just going to get the output. Let me just see the output here. So it just shows 56. So 56, it is not nearing towards 1. So kindly just see that the score we achieved is 0.56, which is not close to 1. So what it is, let me just create or make something as like in comparison. Okay, so comparing the prediction to an actual growth truth, or actual, we can just say actual ground truth. So see here, dear friends, when on just making this, I'm just, yes, in this step, kindly just observe, you are going to look on towards the prediction that is compared to the ground truth. And here, this exact one in this, the first line we just observe, that is the data frame. Okay, and you provide a dictionary as an argument, and the dictionary has two keys. One is actual and the predicted. And actual contains yval, which is actual label in the validation sheet. But kindly just observe, this predicted contains ypredict, which contains the prediction, and one particular thing, both the yvals and y prediction are two-dimensional matrices. So you reshape them to 1D vector by using reshape -1. So which drops the second axis. So the exact second line now causes the interpreter to display the top 5 records as like one is actual and the predictor. So here we have. So I think here this is what we just get from this data set, but actually we have already seen about a demo previous itself. Okay, so now what we have to do, yes, in this exercise we just computed R2 square, that is R2 score, which is an evaluation matrix that can be used for comparing models. And here I just let you know again, this R squared is a statistical measure of how close the data point is fitted to the regression line. It is also known as the coefficient of determination, and this R square is defined by that explained variation that is divided to the total variation that is explained by the linear model. So R squared values always lies between, that is 0 and 1, hence 0 indicates none of the variability of the response data around its mean, and this 1 shows model explains all the variability of the response around its mean. So if you want to just clearly specify, yes, I just let you know one thing. So here, of course, R squared we can just say that is explained variation divided by total variation. And on the other hand, kindly just see here, dear friends, on the other hand, this R squared cannot determine whether the coefficient estimates and predicts are biased. So what we have to do? Yes, we have to make adjusted R square. So this adjusted R square come into the picture, and it has exploratory power of a regression model that has a different number of prediction. Putting it into a simple, let I just give you basically explains the regression. Kindly just to see here, this was our adjusted R square, and here we just go with 1 minus R square with n minus 1 divided by n minus k plus 1. And yes, dear friends, here the adjuster R squared is a modified version of R squared that has been adjusted for number of predictors in the model. So it increases only if we if the new term or a new term improves the model, more than would be expected by chance. So adjusted R square, it's not a typical model for comparing non-linear, but multiple linear regression it can. Okay, yes, fine. So let me just move on to the next one. Okay, here we go with mean absolute error. Dear friends, mean absolute error is an evaluation matrix. Of course, here it is mainly again for regression model. So that measures the absolute distance between your prediction and the ground truth. So the absolute distance is the distance regardless of the sign, whether positive or negative. Yes, of course, whether positive or negative. Okay, so now let I just give you one more example here. So yes, here mean absolute error. Here, for example, let me just have, if my ground truth is 6, if my ground truth value is strict, and you are predicting it as like 5, what is the distance between this? 1. Okay, now however, one more, if you are predicting it as 7, what is the distance between these two? It is minus 1. And kindly just observe, whatever be positive or negative, the absolute distance without taking the signs into consideration is both one as a both case. So this is called exactly magnitude. So the MAE, that is mean absolute error, is computed by summing all the magnitudes and dividing by the number of observation. Okay, so let me just take the same example here. So yes, and here I just want to include an import function that is called mean absolute error. Let I just execute this. It's done. Okay, and next, kindly just observe, dear friends. Here we are just splitting. Okay, and yes, of course, the same thing what we have previously. Yes, we are creating the two things. One is as like futures, and second one it is labels. Okay, and when coming towards this train test split. Okay, so train test split, of course, here for this test size, we have given the ratio as like 80-20. What is 80-20? Of course, 80 it is training data, and 20 it is for testing. And here, yes, the data, that is training data, is contained here in X train for the futures and Y train for the labels. And the evaluation data set is contained in X eval and Y eval. And kindly just to see here the last line. Okay, you split the evaluation data set into validation and testing by using this train test split, because you don't specify the test size, a value of 25%. Okay, so the validation data set is stored here as like X val and Y val, and to the same, yes, the test data, it is stored in X test and Y test. So let I just execute this. Okay, what is the next? Of course, we have to create a model, and yes, let us have our prediction also. We have to prediction our data validation data set. So here we just create it, and of course you make use of that predict. Okay, so yes, we are fitting it into that model. Yes, it is all comes at linear regression. Okay, and next it is all about predict. So you make use of this predict method to predict on your data. So in this case, you are passing xval, okay, as a parameter to the function, and recall that xval is your validation data set. Okay, the result is assigned, and you are going to call it as like y prediction, and will be used in our next computation. So let I just execute this. And what is the next one? Of course, we are just going to create this mean absolute error. Mean absolute error we have to compute. And yes, dear friend, we have already in this data set, I just want to specify one thing. This mean absolute error, you are passing y-val and y prediction. Okay, so y-val here and y prediction, which is the exact label that was provided with your training data, and y prediction, it is the prediction from the model. Okay, so let me just execute. I just execute this, and I just check here the value. Okay, 0.7243. Okay, both y value and y prediction, of course, by using this numpy array that contains the same number of element. So the mean absolute error function subtracts it, and we are just getting. Okay, so let just we have the same thing in our new array. So the element in the resulting array have the same absolute function applied to them. Okay, so all the negative signs are dropped here. So the average of the element, that was computed here, and we just got 0.72. Okay, what is the R score? So let we have the R score. Of course, it is 0.56. And kindly, one thing, dear friends, this MAE and R square score may vary depending on the distribution of the data set. A higher R square means a better module. A higher R square means a better model, and uses an equation that computes the coefficient of determination. Okay, what is now? Of course, we are not having the higher R square. What let we just do? Okay, we let create one more model. Okay, and let we compute that MAE. Okay, so we have calculated MAE, which is significant parameter when it comes to evaluation model. Okay, now you will now train a second model and compare it to R square and MAE to the first model which we evaluated, which is better performing. Okay, so let we create here. Okay, and here we make use of a pipeline to quickly transform our futures. Okay, so quickly transform our futures and engineering new future using this minimax scalar. And there's polynomial future and there's minimax scalar. That is, it just minimax scalar reduces the variance in your data by adjusting all values to the ranges that is between 0 and 1. So it does this by subtracting the mean of the data and dividing by the range. So which is minimum value subtracted from the maximum value. And here polynomial future, yes, will engineer new future by raising the value in column up to a certain power and create new column in your data frame to accommodate them. So yes, let me just create or read the exact first data here. First of all, let me have the same data only. Okay, so we are just having that data, and okay, I just specified. Okay, so here it is our data, and yes, dear friend, when we just have this, of course, we, as I have already specified, it is with semicolon, that is the separator. Okay, and next, that exact data frame which we just specified as DF, now we are splitting it into futures and labels. So here, previously we just specified it as like a future label. Here futures and label, that is what the difference. So the thing making for this second one. And next, the exact line which we have here, it is, yes, of course, the same, to split it, the futures and labels into 4 set. as like X train, Y train, X evaluation and Y evaluation, and containing the same. So 20% of test data, and yes, what we have just specified here, it is as like 8 years training data. Now going on to this, I just want to specify. So here in this step, you begin by creating a Python list called steps. Okay, so this list contains 3 tuples, each one representing the transformation of this model. The first tuple represents the scaling operation. So here the first item in the tuple is the name of the steps, that is the scalar. And this uses minimax scalar to transform the data. So the second, it is all about the poly, named as poly. So creates additional features by crossing the columns of the data up to the degree that you specify. And here in this case, you specify here as like 2. So it crosses this column up to a power of 2. And yes, next the model. So it is the linear regression. So let I execute it. And what happened? Minimax. Okay, minimax, whether I am not, let I just, oh, sorry, I didn't execute this. So once on execution, so let I just execute this. Yes, it's done. Yes, dear friends. So in this line, you are going to create an pipeline and store it in a variable called model. Okay, the pipeline performs a series of transformations which are specified in the step you defined here previously. Okay, so these operations work because the transformation minimax, scalar and polynomial features implement 2 methods called fit and fit transform. So you may recall from previously we have already discussed about this. Okay, so how to train by using the fit or fit method, fit and transform method. Okay, so here we are just going to with fit. So I execute this and coming towards this. Okay, so kindly just observe how the model here it is. So minimax, scalar, and we just got it. And here I just want to specify things. So when on making towards this is what our training model, I just to show you again. So this is the exact, the training the model. And what's next? Of course, we have to predict using the validation data set. Let me just make it and compute the mean absolute error. Compute the mean absolute error again towards the R squared. And kindly just to see the last that you compute at this step is called the validation loss, because you may use the validation data set. This exact difference from the training loss that is computed using the training data set. So this distinction is important to note as you study other documents or other things. Kindly just other resource whichever we have already discussed. So kindly just see here, dear friends, at this point you should see the difference between R square and the MAE of the first model and the second model. What is it? Yes, in this thing you engineered a new feature that gives you a model with a hypothesis of higher polynomial degree. So this model should perform better than the model up to a certain point. After engineering and training the new model, you computed the R square and MAE, which you can use to compare this model with the model you trained, which is previously. So yes, we can conclude that this model is better as it has a higher R square. Is it so? No, actually here it is 66 and 62. So if we tune furthermore, yeah, I think we can get higher R square. So even though from the previous one we have lowered the MAE and yes, higher R square and lower MAE, we can just make it here. R square has been increased and MAE has been decreased. Okay, so yes, we would evaluate each and everything and we tune up furthermore to make an better model. Okay, so next let me just move on to the other metrics. Okay, other evaluation. So what is next? It is all about mean square error. Okay, so mean square error. It is very much interesting. So what is mean square error? It is, yes dear friends, this is minor difference between mean square and mean absolute error. That is, deviation comes in, mean square error takes the average of the square of the difference between the original value and the predicted value. And in mean square error, the computation of gradient becomes easier than mean absolute error, which requires actually computation tools is in order to compute the gradients. Okay, so yes, for you I just specify here, that is mean square error. Here I just specify, yes, it is 1 by n summation of everything, ji to n, and of course this is what we specify as like original value and towards the predicted value. And kindly just dear friends, one thing, mean square error is good to use when the target column is normally distributed around the mean value. So mean square error comes into the picture when outliers are present in our data set and it becomes necessary to penalize them. Okay, yes, fine. So let me just have the example here. So here we are just going to calculate it with mean square error. So let I just import it and I am just calculating it. And added to this, I have just specified this root mean square error. What is that root mean square error? So let I just give you. So here I specify this is mean square error, and here it is 1 by n summation of j is equal to 1 to n, and yes, original minus predicted the whole square. And what about root mean square? Of course, the root of this MSC, that is RMSC. So yeah, you can just specify as like 1 by n summation of j to 1 to n and yj. Okay, so here I specify j. Okay, yj minus yj mean the whole square. So this is what root mean square. And dear friends, I just want to give you a detailed thing about this root mean square error. So this root mean square error, yes, it is most popular matrix in regression problem, regression model. So this root mean square error is defined by the standard deviation of prediction error. Okay, so this is what. And here this prediction error are sometimes called residuals also. So it is very much important. So residuals are basically the measurement of the distance of data points from the regression line. And yes, dear friends, here we are summing up. And what is the exact summing up? Of course, the original and towards the prediction, that is squared. And here we have n samples. So putting it in a simple way, this RMSC tells you how well the concentration of data points around the regression lines. So with RMSC, it is assumed that is residuals are unbiased and follow a normal distribution. Here I just want to add up some more important point, dear friends, that is this RMSC works efficiently when we are dealing with a large volume of data points. So hence error reconstructions becomes more reliable. And next one, as per RMSC mathematical formula, here we are using square root, which shows, yes, large number deviation. Here large volume, here large number deviation. And next, before using RMSC, be sure that there are no outliers in the data set, because RMSC is heavily influenced by outliers. Think about outliers. Okay, last but not least, root mean square error has higher weightage and it is also penalizes error as compared to other evaluation metrics. So kindly just be aware of this, dear friends. And let me just go with the next one. Sorry. Yes. An important thing. mean square log error. Of course, I have just written here. So let I remove this. Okay, so here mean square log error. This as the exact name implies is, if we kindly just see here, root mean squared logarithmic error has a log of actual value unto that predicted value. So this type of evaluation matrix is used when we don't want to penalize. When we don't want to penalize huge things. So here, of course, I just want to specify one thing. Let I explain the exact data, then I just come here. So if you are making use of this RMSC, what you just specify here, 1 by n summation of let anything I or j 1 to n, so total number of samples, and here you specify that actual minus prediction the whole square. So this is what you specify in RMSC. And when you just say to this log error, that is root mean square log error. Okay, so we just specify it in, sorry, RMSLE. So this is what. So here the same thing comes here, root of 1 by n, the same summation. So I is equal to 1 towards n. And kindly just observe here, dear friends. Here we are subtracting it with the prediction. This comes here first. So I'm just going to make it as log of pi plus 1. Okay, minus this one. So this is actual, this is prediction, and here the prediction what we just have, log of it is a prediction ai plus 1, and here the whole square. Okay, so this is how a huge difference in that prediction and to that actual value, and this predicted and actual values are considered to be huge numbers. Okay, so this is what when you just make use of it. And let I just see the exact value. Okay, so yes, as I have already specified, yes, the mean logarithmic error, this introduce this logarithmic, okay, so into the equation by adding 1 to both the ground truth and prediction before taking the logarithmic. So then the squaring the difference. So then summing them and dividing by the number of observations. That is what it happens. So this mean square logarithmic error has the property of having a lower cost of prediction that are above the ground truth than for those that are of below it. Okay, so let I execute it. So here we have MSC, it is 0.77, RMSC it is 88, and here we have 0.43. Okay, so 0.43, that is what we have a lower cost for prediction that are both the ground truth than for those that are below it. Okay, yes, dear friends. Okay, so yes, here we are we have discussed a lot in this. Of course, we also discussed about the splitting our evaluation data set into two, and because of X test and Y test are used once for final evaluation of the model performance, and you can make use of them before putting your model into production. And to see how the model would perform in production environment, yeah, you have learned how to access the assess the quality of the regression model by observing how the loss changes. And of course, we discussed with an example using MAE, and also learned of that existence MSC, RMSC, and MSLE. Okay, and yes, dear friends, so coming to the end, if you found this video helpful, don't forget to hit the like button, subscribe to the channel, and turn on notifications so you don't miss any of my upcoming videos and contents. And yes, dear friends, drop a comment below if you have any questions or suggestion for future topics. And as always, keep learning and stay curious. See you in next video. Happy learning, dear friends.